the opportunity to introduce the honored guest. Professor Mo Jamshidi received his PhD degree in electrical engineering from the University of Illinois at Urbana-Champaign. He holds 3 honorary doctorate degrees, including one from the University of Waterloo, Canada, with which DEA has signed a memorandum of understanding. Currently, he is the Richard Brown Endowed Chair Professor at the Department of Electrical and Computer Engineering at University of Texas at San Antonio, USA. He has also been the founding director of Center for Autonomous Control Engineering at the University of New Mexico. He was a senior research advisor at U.S. Air Force Research Laboratory, New Mexico, and consultant with the U.S. Department of Energy Office of Industrial Technologies and Department of Energy Laboratories. He was also an advisor for the NASA headquarters on NASA's Pathfinder project mission and Surface Systems Track Review Board. He has over 600 technical publications, including 62 books, research volumes, and edited volumes. His most recent edited book is on System of Systems Engineering. He is the founding editor or editor-in-chief of 5 journals, including IEEE Control Systems Magazine and the IEEE Systems Journal. Dr. Jamshidi is a fellow or member of 8 societies and academies and has received numerous awards and honors. He is currently on the board of governors of the IEEE Society on Systems, Man and Cybernetics and the IEEE Systems Council.
Thank you very much, Professor Das, and ladies and gentlemen. I would like to discuss with you one of my passions. For the past 5 years, I have been advocating a new branch of engineering, which is an extension of systems engineering. And that I call System of Systems Engineering. And you can contact me at emails here. And we have my research lab is here, my IEEE System Journal is here, my IEEE System of System Engineering Conference is here, and another congress I have, another journal, and so forth and so on. So I have many activities. Okay, so I would like to introduce to you what is System of Systems, what are the challenges, what are the innovations. And then I'll talk about control engineering, because that's my area which we are trying to progress, controlling a number of systems which are wirelessly connected together. They're not connected by wire, only wirelessly, which is very difficult in itself. Then I will talk about our activities at the University of Texas. I hope to have some conclusions and some movie clips. And then I'll talk about the workshop which we had, we just came from at the IIT Kanpur. We had a workshop sponsored by the Indo-US Forum on Science and Technology on System of System Engineering. And I'm very happy that System of System Engineering is getting a good start in India. You'll hear about it later. So, as you know, since 1995, Internet has connected the people of the world. There's hardly anybody who is not using in a scientific work or even financial, commercial, and other world, Internet. Internet is connecting people together. System of System is a generalization of this connectivity of systems or systems and people. So we want to have systems talking to each other, okay? And it's possible that we have people connected to the systems, okay? And therefore, System of System, SOS, is getting into new application cases in a very persistent pace, from information technology to defense, to energy, to space, to environment, healthcare, to services, earth sciences, and so forth and so on. So one definition of system is a system which consists of an integration of independent, non-homogeneous systems which have a unified goal. The goal is to improve performance, minimize cost, increase robustness, increase reliability. So traditionally, a lot of systems are working independently by themselves. The concept of system is to have them work together for a good cause, mostly for a good cause, okay? And that you'll see later many potential cases. And because of that, it has many applications in defense, in energy, in environment, in automation, and so forth. So what I would like to make clear to our friends in engineering field is that system engineering versus system of system engineering. What are the difference between the two? System engineering is a discipline which is at least 5 decades old. But system of system engineering at its present situation is only an opportunity. Meaning that we have a long way to go from system of system to system of system engineering, because a lot of issues are not resolved. Theory and application are not resolved. So, for example, here you see scholastic hits on the Google up to the year 2005 on system of system versus system of system engineering. The system of system hits are exponentially blowing up to large numbers, in this case around 400. And then in system of system engineering, at that time, it was very low. So you see the big gap between system of system engineering and challenges which are involved here. It's our duty, it's my challenge, and people around the world is to close this gap between these two. Okay. Recently, I Googled in this concept myself, and system of system is still over 1.5 million. This one in thousands. Okay, in only a few thousands. And if you Google system of system and my name, you get about 10,000 hits. Okay, and a lot of them is not relevant to system of system engineering. So here is system of systems. In order to go from system of system to engineering of system, everything has to change. Modeling is a brand new idea, because you cannot model a system which mathematical representation is not possible. You just have communication links between the two. Simulation, emergence, architecture, control, cybersecurity, network centricity, ethics, all of these issues have to be reckoned with, has to be discussed, and a lot of smart people have to work for these problems. So what are the examples of this? Here is an example of the military example of system. In many applications in defense, especially in the United States, you have a small stovepipes up to large stovepipes, which are sort of a few systems here, a few systems there, a few systems here, a few systems here, but they're not really into one umbrella, one together. What you want to do is to couple them loosely and tightly, integrate them into what we call a network. So you put a network all the way around. Everything you see there, you can put them all together here. Okay, so this will allow American Army, American Navy, Air Force to work together, to put all their resources together. Okay, so the word system of system is not my idea, my terminology. It's the Department of Defense of United States. You know, my colleague Dr. Sahni, who was in Kanpur, heard a presentation of our friend Mr. Wilbur from Boeing. As you know, Boeing is trying to put a 787 aircraft into market with problems, and the system of system for that aircraft is called E-enable. E-enable meaning that this aircraft could have problems in the air. It's connected by satellite and by ground to all the other aircrafts and the control tower, and then the system of system from the cockpit, it will delay these things and warn them about the problem. The people on the ground know what is wrong with the aircraft before it arrives. And they make the parts ready, mechanics are ready, and when the aircraft comes, they fix it. Okay, so this will be an integral part of. Another application of that is what we call Earth sciences, a global Earth observation system of system. Since the tsunami disaster we had in Asia, including India, the world has now been connected by a system of warning system to give the early warning to countries like India to go into the land so the tsunami will not come and basically damage and get the lives of so many people. Okay, so airport is a system of system, consists of baggage handling system, air control tower, plane with crew, freight, reservation, etc. So the entire airport is a system of system. One aircraft is not a system of system, it's only one system. But the airport is a system of system. So is air traffic control. Going from one airport to another airport is a system of system which is help route the traffic, monitors the aircraft. Energy, green energy, solar power, wind tower, you can connect them together either by wire or by wireless, connect them together like this. Here is an oil production system of system. You have production system, logistic, refining, distribution, use. There are 1, 2, 3, 4, 5 system of system working together. So system of system, you can also use the concept for managing them, to make management more efficient. And that will save a lot of money. Here is a picture of a smart grid. A smart grid energy system of system. Here is, let's imagine that's your home. You have a large parcel of land in your home. You have a wind tower. You have solar panel. You have many appliances. And you have your car and so forth. And you have a home area network, a wireless network at home. Then you also have smart meters, which monitors the expenditure of energy in all your equipment in the house. And this smart meter is connected to the local area network, which could be province of Agra. And then it will go to the, let's say, northern grid of northern India, and this goes the entire Republic of India. Okay? So it can go from your home all the way to the Republic of India. It's network connected together. This whole thing is a system of system. The objective is to make energy production, energy monitoring all automated. Okay? If you want to go to Mars or Moon, you can also use system of system for a space exploration. System of system approach for human space exploration. And these are, this is the Moon, this is Earth, these are the rockets and the vehicles which takes experiment and humans to the Moon. So the entire group is a system of system. And these are all written in a chapter of one of my books, which I will talk about later on. Modeling and simulation is another, needs to be changed. Therefore, you have to look at model a system where the mathematical representation of the constituency of the system are not physically available. Newton's law doesn't work. You don't have time for it. You know, thermodynamics doesn't work. All you have is data going from system X to system Y. And that data is the only information you have. That data coming out of system X is the behavior of the model of the system at that instant of time. And there you need to make the most of it, of that information. So the philosophy of modeling has to change. That's the point I'm trying to make. This is an application of the situation where a system of system is used for recognizing a submarine which may belong to the enemy, And so all these parts of a system are friendly system, but this particular system belongs to the enemy. So in this case, you have not one goal, but you have two goals. The goal of this system is to find it. The system of this is to hide from the other enemy. Okay? So this is the situation where you have work done by two different groups. This was part of one of my PhD students, Dr. Sridhar, a native of Bangalore, who's now working for Microsoft in Washington, the state of Washington. This is another application of system in air transportation system. Every red dot you see here is one aircraft in the space of United States. And this is a visualization of 2004 air capacity network for the United States. This is a healthcare system, where you have managed care companies, you have hospitals, you have patients, you have pharmaceuticals, you have regulatory agency and government, clinics and nursing homes, physicians. You have to connect them all together. And unfortunately, this is another example where you have contradictory goals. Okay? At least in America, the doctors and patients need to have good care. The companies, the insurance companies, they don't like to give it. They like to just make money. Okay? They would rather that you never get sick. Okay? This is now a summary of what we are doing in Texas. Our research areas are air, land, and sea rovers. This is our air, land, and sea rovers. We have rovers which work under the water, as well as, see, my colleagues are joining me from the hotel, with one exception. Then you have green energy activities, and another area which we recently started, cloud computing. Okay. So, as I promised, I want to emphasize on the control aspects of system, because that's my field. I've been a control engineer for roughly 42 years. So, the control engineering, like any other field of system engineering, is being pushed and being challenged to deal with systems which are not physically together. They are wirelessly connected. They may not even be on the same planet. Okay? They may be miles and miles and lots of distances away from each other. What makes it difficult for that system to be controlled is that a lot of information is going from far away places. Not everything is sensed right on board on the system. Okay? So you have basically an ad hoc wireless network in your feedback loop, which can be anywhere. This is a sort of a pictorial of the same concept, where you have 4 systems as a system of system, 4 actuators, 4 set of sensors, 4 controllers, which have communication channel or wireless connections and physical connections. And you can see that some of the controllers are using information from other systems to control their system. And this was the subject of a PhD student at Caltech a few years back. So how many different control paradigms are possible? Hierarchical, decentralized, consensus-based, and network. I will briefly go through some of these. Hierarchical control has been around since basically 70s. Mezarovich at Case Western Reserve came up with the idea of hierarchical control, where you basically look at subsystems of a given system. From the top, their solution gets coordinated. From the bottom, they have isolated solutions. And by exchanging information at levels, you iterate enough time to get a feasible and optimal solution. And in this case, a system is chosen to play the role of a coordinator. Each system receives its n-1 neighbors data via wireless communication through this. And then an optimal control is designed for each system. By coordinating this n solution by some iterative algorithm, through this communication, repetition of communication information, you come up with a solution. I'm going to skip this because it's all optimal control theory. And here is an example. Suppose you have 4 rovers. This happens to be one which is developed as JPL at NASA. This is a commercial Pioneer robot. These are some of the robots we built ourselves in Texas. And here is essentially a depiction of that 4 system of system. Example, here's 1, 2, 3, 4 system. Some of them are wirelessly connected, as you can see here, but a lot of information are shared by wireless communication. So we go through the mathematical representation, which is assumed to be linear, time invariant, which itself is far from reality. But eventually, through a hierarchical control algorithm, communication error goes to 0. And these 4 systems establish a normal channel of communication among themselves. At that point, system has to be stable and has to give you the goal that you have been seeking to connect them together in the first place. These are some of the simulation results on MATLAB and Simulink. And you can also do it decentralized or distributed control. Basically, you have n local controllers, which you use wired interactions, wires connection, but you also have a global controller which uses wireless interactions, which will help give you additional control component, which is based on wireless information, neighboring systems. We call that global control. So a combination of local and global control will help you, and you can actually show, depending on the amount of delay in the wireless connection and behavior of these controllability and observability properties of the system, you can see that this system can be stabilized, would become stable. A simulation of this was done by one of my students at Kanpur, Dr. Anjan Kumar, soon to be called doctor, and this is the objective function. These are the dynamics of n of those. This is the solution to the optimal decentralized controller, and these are some simulation results. Consensus-based is an area which my colleague Dr. Hadieh from JPL has been pushing for another system of system which he calls, and now is becoming very popular terminology, formation flying systems. And basically, you can bring telescopes, you can bring, let's say, many different space vehicles into one formation, which will allow you to do a lot of good things that single one of them cannot do for you. So consensus-based has been used for that in what we call cooperative control mode. And in our case, we used it for underwater vehicles. Applications of underwater vehicles are, for example, going through this consensus communication among them. Multiple rovers are involved. No single controller unit or rover can do all the job. Units must agree on a goal. Sub-goals may be different for each unit, and you have to share communication among yourselves. So here is that some of the potential applications from large ship, which you need to detect potential problems, detect maybe attacks or bombs or what have you. No single diver can do these jobs. The single inspection robot cannot do that, and it may be even too slow. So you want a swarm of cooperative inspection rovers, which automated, for example, video arrays, which could go around it. This is a video array robot. We have 2 of those in Texas, and this is an autonomous one which we built ourselves. And so we have 2 different kinds of underwater rovers. Here is the communication protocol for consensus-based. You basically, each vehicle has a token, has an ID. It starts with the lowest ID, and then the communication from that single one goes to the next one, and the token is lost. Okay? And then goes to the next and the next. Ideally, you like to have a complete three-talk three-way talk directly. But normally you cannot do that, so some of them may not even get the information. So that's what makes the job of control very difficult. When you go through the cycles of from one token passed from one vehicle to the next and the next, you eventually look at an index called J, which needs to be driven to 0. In this case, the formation is that the rovers are going to be equally distanced after each other. They might go through a pattern like a circle or a line or something, but they are going to be following each other. And then you will have, and this is what I was just mentioning about token going from one to the other. Then every 1/10 of a second, you have one transmission between one rover to another rover and so forth. And then you basically come to the point where if you want to increase the speed of the rovers, you shorten the distance and they move faster and faster. Here is a simulation of that scenario, with a combination of a real video array submarine and simulated ones. Those in the circle down here, those two are real UAVs. And the other, I mean, not UAV, UWVs, and the rest are simulated UWVs. And we did that for different depths. They all have different depths. And we use consensus-based control to run this controller. And now here's the network control. Network control is an integration of cyberspace and physical space, as it is in other ways. But due to wireless nature of network control system, complexity and cost can reduce to some extent, because those complications can be reduced because the information that you normally want to go from one system to another goes through the communication channel. You don't have to dynamically represent it in the model, for example. And this can also be modified. You have a situation, as we said, that the control loops are closed through a real-time network. That makes it so tough. And sharing data among controllers enables these systems to fuse global information to make intelligent decisions over large physical spaces. This comes from Wikipedia. Here's a block diagram of a typical network control system. Here's one system. It has sampler. You have information coming from sensors. Some of the sensors are connected back to the system, but some are, this dotted one goes through an ad hoc network. And that ad hoc network has nodes on the sensors, on the actual controllers. It also has nodes from other systems, I-1, I+1, and so forth. The controller, after a time delay, receives the information from the sensors. It does its own implementation of control laws and sends it to the network through a time delay from controller to actuator, which is on the plant. Therefore, you have two delays. We call it forward delay and backward delay. And they are two different animals. They cannot be treated the same way. As you will see, the backward delay can be handled by a Smith predictor. This one has to be done by non-Gaussian distribution of noise, which we call it Levy's alpha stable distribution. And the communications could be by field buses, control area network, local operating network, LON, could be Ethernet, could be Bluetooth, could be Zigbee, and so forth. And my students are actually using most of these in the lab right now. And these are the applications of network control, which you already have seen it. In some situations, the time delay is such that it is random. If these systems are on the internet, and we are all in this room are using the internet, keeping the net very busy, obviously the time delay is too much. So you have a burst of delays, depending on the time of the day, how many people are using their computers. So one way to deal with that traffic jam or saturation of data coming in, or you need to slow down the sampler to make sure the data is all clear through the network before the next sample. Okay, this will give the chance, so-called, for the system to be read and revive itself. So here is another block diagram of a network which is controlling a whole bunch of systems and hosting controllers, hosting systems and sensors and so forth. So what are the technical issues on network control system? Some of the most important technical issues are scheduling of the communication protocol, network-induced delays, which we just talked about, design of the controller, which happens to be actually not a big issue as long as these problems are solved, the stability of network control system based on time delay. Theory is, fortunately for this problem, theory is there. You can actually have the delay in the network to be less than an upper limit to guarantee stability. Okay? Actually, I'm teaching that in my classes in this semester. And this is what I was talking about, the forward delay. Forward delay has to be estimated using alpha stable distribution of noise. This is a theory which came into the mathematical world by a mathematician called Lewis in the 1930s. Okay? This used estimation of network-induced delay. For my students, before I taught them network control, I had to teach them control, modern control, time delay control, and then bring them into real network control issue. This is, let's say you have a plant here, you have a controller, in this case it's a PI controller, and you have a delay. Unfortunately, delays are not lumped. They're not lumped value, which you can put your fingers on it. It's distributed. It's random. It's very difficult in network control system, which is a candidate for system of systems. Without the delay, the system is well behaved because of the location of the poles, and without this delay, without this. But when you add the delay, system becomes unstable. That's what we are trying to avoid in real-time system of system control. What we did next is to approximate that time delay by what we call Padé approximation. We got the same behavior. Next, we used a Smith predictor to reduce the effect of the delay. A Smith predictor works like this. You come up with a model of the plant, you come up with a model of the delay, and you find the difference and you feed that back. This came into a control engineer by the name of Smith in, I think, United Kingdom in 1957. So we implemented that. This is an application of it on Simulink, and we stabilized the system. You can see we went from this to this. Okay. Now, if we put an adaptive loop on it, which is shown also here, we have, here's your plant, here's your Smith predictor, here's all the logics and dynamics for the adaptation using least mean square minimization, sort of like gradient approach for estimating the value of the delay. We then were able to actually play around with various different delays, and each time the system remains stable. From 1.8 seconds to 12 seconds to 300 seconds to a random variable, which is like this, the system is still fairly stable. Next thing what we will do, we'll make that delay follow a non-Gaussian noise, namely alpha stable. This is typically how you can represent the delay in a computer network, like your internet use. You see, these are the bursts I was talking about. Okay. Now, there is a parameter called alpha. If alpha is equal to 2, this becomes Gaussian. So Gaussian is a special case of alpha stable distribution. Now, let me show you some of the projects we are doing in Texas. And since I've been in Texas for the past 4 years, we have been host to a number of international students, including Anjan Kumar from Kanpur, who came for 8 months to San Antonio and worked with my students. And one of the advantages he got from his experience, he got his hands on the hardware a lot. He learned everything inside out from GPS. And he developed a lot of things using GPS. So what we do in Texas, in my students, we buy a basic vehicle which has just 4 motors, and we load it up with our own electronics, our own sensors. This becomes our finished product. This is a swarm of robots, which will eventually have 26 of those, which are wirelessly connected together by Zigbee, and they are connected by one single laptop. And they have consensus communication among them. Okay. This is a picture from our underwater robots, which was built by, painted by my student from Australia, another visitor, Matthew Jordan. Here's the inside that his underwater robot. This is the guts of it, and has a single board computer in a plastic tube, which is the main body of the underwater robot. Here's the characteristic of it: very low cost, under $500. Obstacle detection avoidance sensors, has external inertial navigation, and inter-robot communication. They're all there. I'll skip this. These are some of the scenes from our application in the swimming pool. I might also add that our video rays have been tested and worked in Alaska, in Pacific Ocean, off of the coast of Hawaii, in the Gulf of Mexico, and many lakes in Texas. So we have also gone into real oceans, real water. Here is a scene from some of the students. In fact, you see 3 Indian students are there. This is my PhD student, Kranti Manoj. I think he's from Bengal, who is now, his master's was underwater communication. And now he's doing his PhD on cloud computing. Here is another scene. Here is myself, which I also go there. I used to be a novice diver. I went there and helped the students. When they finished the experiment, then I swim for exercise. Not bad. Again, this is another scene of the rovers in action. Students are working. And here's a laptop which is connected to the underwater robot, and there you can see under the sea with the various cameras which are connected. This is a torpedo, a small mechanical electronic torpedo, electronic fish, which we use it for obstacle under the water to avoid by the rover. This is a scene from a public broadcasting system television show in Texas, which I'll show it to you later on in the movie. Here's another Indian student who built this robot by himself, Vikram Raghavan, who is now working for an oil company in Houston. He's building a robot to go into the oil pipe to look for leaks of oil. Isn't that fantastic? Unfortunately, he was so good, he was absorbed, I couldn't afford him anymore to keep him as a PhD student. So I'll show you this movie later on, so we'll worry about that later. And we also now in the air, here are we have fixed wing aircrafts, we have quad rotors, and we want to actually, we have several GPS modems on it. These are the information. We have one which is 80-inch wingspan, 70-inch wingspan, wing area, and so forth and so on. And so some of them have, most of them have gum stick control board on it. They also have autopilot. One of them even has autopilot, where we can not worry about keeping it stable up there. We can do experiments. And objective is to have a swarm of UAVs. We want to have them do autonomous flight, and we want to have consensus-based controlling them as a formation. This is the first flight of our first UAV. This is a scene from a corner of our lab. We have the UAVs, we have Land Rovers, we have underwater robots, and so forth. And this young man is Aldo Jaime, a student from Bolivia, who is heading the group of UAVs. This is a UAV actual test. We did it, and you'll see a movie of it later on, which also is on YouTube. This is a recent simulation of consensus-based control of the formation of UAVs. Here, the blue ones are 3 UAVs. The red parts are obstacles and other things going on in the air. Then the consensus has been established among these 3 UAVs, and they create a formation. Then we have waypoints here and other places where the formation goes there first, like so, or they come back to here to another location. And what we want to do now is to do it in real-time application, because we have 3 UAVs. We can put it all in the air. Eventually, we also want the UAV to talk to the Land Rover through communication link. We also use fuzzy logic to control some of these UAVs. This is a fuzzy logic controller, which is done on Simulink for implementing on IMUs on the gum stick inside the UAV. We also are building our own UAV. We a group of students for about maybe $4,000 or $5,000. We also put a generator on it. We have onboard energy generation. And we want to send a team to a national competition next year to compete against other student group like Stanford or other universities, to compete with them with UAV competition. And here's a design picture of their design. And it's much further than I show it to you. A lot of things have already been built. Our recent activity is green energy, solar and wind, and soon fuel cell as well. What we want to do is to get a solar system, a wind tower, connect them together wirelessly, and put their DC voltages in a battery stored. Then it can be inverted to AC through an inverter, which comes with a package, and then you can energize a building on the campus. Or you can also connect it to the grid. Okay? This system will be built in about a month or 2 in San Antonio. More recently, in fact, we have a proposal due tomorrow in Texas for over $1 million from a state of Texas. We are asking them for $1 million to generate 187 kilowatt hour of energy, green energy on campus. And that will be enough to energize University Center number 3, a student union building, and expanded of our previous designed offices of the campus. So, and of course, we are all going to be connected together, and then we have a control center for the entire network control of this energy producing system. And we use LabVIEW of National Instrument to check everything, from wind direction to wind velocity to solar radiation to all the currents, all the voltages, to see what's going on with the system continuously. And we may have 2 control indicators, one in the big building, one in the other smaller location. And this is the location we're going to build. We're going to build the system here. This is one of the smaller buildings we are energizing, and this is where we can control it wirelessly from remote. We're going to connect it into the Ethernet of the university. Now, what is cloud computing? This is our last area of research. Is an extension of computer systems to virtually make available to you a lot of computing power which you can rent for hourly basis. If you have a big problem you want to solve here in Agra, you don't need to buy a computer. You can buy time on somebody's server, which could be in Singapore. And you can borrow software for 1 hour for some computer, some server which is in Hungary, in Europe. That's the idea of having a cloud among all these things. I have 2 PhD students and a bunch of undergraduates who are actually physically connecting these computers in the lab right now. Okay, and we have hardware and software all combined. So we then run a test, run a problem which uses the resources of all these, with no single one of them can do the job. You borrow the information from others. This is called cloud computing or grid computing, someone calls it, or someone even call it utility computing, autonomic computing, and so forth. So you share resource, hardware and software, both. For example, you could have Microsoft, Amazon, Yahoo, Google, all sharing a big number of sensors together. One of the reasons we want to do research in that area, because what happens, and here's another cartoon, what happens in the cloud is that when you need resources, somebody has to physically, a technician, has to put 1 or 2 or 5 servers online. We want to eliminate that operator. We want to use feedback theory, automatic feedback control, to do this automated. Okay, that's the idea. You could have a whole bunch of servers connected. You can just trip their relays and put them into line. Okay, things like that. In my own personal persuasion of pushing this technology worldwide, I've gone from Texas all the way to Australia to do many workshops like the one in Kanpur. I've had similar one in Spain. I've had one in Argentina by way of video conferencing, one in Australia, and so forth and so on. And in the meantime, I have established an IEEE conference on the subject. It's been in the United States 4 times. Now next June, it will be in Loughborough, United Kingdom. Loughborough University is one of the universities in UK, in England, which is very active in system of systems. And I'm going to be there. And then, of course, I also have my own IEEE Systems Council participation and the journal which Professor Das mentioned I have established. Here is the conference in Loughborough, which Professor Behera is part of the team. And I hope that some of the colleagues from AGRA will actually submit papers, okay? And we'll try to find money to travel, okay? Maybe from Royal Academy of Engineering and other group. The British took a lot of advantage of India. They have to pay a lot of things back, okay? Here is the 2 system of systems books, which I published in 2008 and 2009. And I have a book series, which I can also publish books in this area. Anybody interested to do a book, I can easily tell you how to do. And this is a history of systems in one of the issues of my IEEE journal from last year. In 2007, I established a consortium called International Consortium on System of Systems, where I put academic institutions and industry together to look at some problems. And I also invite international partners like India, Hungary, UK, Spain, Mexico, and so forth, and national academies and government. The idea is for the funding agencies to come and look what we are talking about without asking for money. Once they understand what we are doing, they get excited. They go back to their offices. They put money in our ideas. Then we are ready to apply. You see? That's the idea. But when I try to sell that idea to the industry in America, they say, no, we don't want to be part of that. It's called international. We don't want to be international. We are worried about security, about ITAR and so forth, okay? Export control and so forth. So now I'm doing a US system of system network, which IEEE and INCOSE, 2 important system engineering organizations, will be involved. Purdue University, George Mason, MIT, our own university, Stevens. Others are Georgia Tech, University of Miami, Naval Postgraduate School, Old Dominion, and University of Southern California. I'm bringing a lot of important players in America into this network. And so far we have written a white paper which tells you what we want to do. What do we want to do? Number one, we want to close that gap between engineering and the concept. Remember that gap? We want to close that gap. Put theory in there, algorithms in it, technology in it, to make it a reality, a full-fledged, genuine engineering field. We also want to have produce the future engineers for this technology. Because those technologies, believe it or not, cannot be brought from any part of the world, including India or China or Europe and anywhere. Everybody is on the same page right now. United States may be a little bit higher ahead of the others, but that's about it. Okay? Because a lot of technologies which are developed could be in defense environment, which may not get transferred or into real civilian case quickly enough. Again, these are the areas we need help. So if you are excited from system of system concept here in Agra, I want you to help him in one of these areas or any other one that you can help. In conclusion, I want to tell you that system of system has been with us. It's nothing new, but connecting them together has become a reality because of the internet. Okay, internet has been a big server, a big service to the people on planet Earth. Network control is probably the best possibility, but it's not quite proven yet. And there are too many applications, lots of applications. Control and AI communities and many others need to help, especially communication community. Once again, I want to remind you, system of system engineering is not an engineering field because there are tons of problems. It's only an opportunity. So at this point, I would like to show some movies. Yeah, this was what our piece was part of 9 other UT schools. This was produced in Austin, Texas. This is my younger brother.
We're learning that some San Antonio students could possibly play a key role in preventing more U.S. deaths in Iraq.
And it's all because of a robot.
Hoping to take luck out of the equation is a group of UTSA engineering students who have designed and built robots that sniff out bombs and biological weapons.
Robots can move, they are mobile, but the
system if the end is everything.
let me, I'm going to.
We have a demonstration
This
of
is Dr. Sridhar.
robots working in
We put fire or a small fire in one corner of the building.
One of the sensors will
Here.
be
And
reporting
then
a fire.
this
in the
one
field.
picked up by the big
Temperature
robot.
Will change drastically. That's going to be picked up by the master robot that there is a trouble out there.
That's the master robot.
The robot is actually looking at the sensors. It is registering the change in temperature.
Which is here.
The master or the coordinator robot will communicate with the scout robot and send the scout
This is
robot to the
GPS,
trouble spot.
communication.
The scout robot is right now spinning its wheel, turning around to calibrate through the GPS coordinates.
Command robot takes the GPS locations and it then sends it to a swarm robot to go check out the most dangerous threat.
Now it went to find it.
Like say
It
if
found
there
it
was
and went there.
an industrial plant and they had a heat leak, the sensor would pick that up and the swarm robot could go to that sensor.
So here is, I'm going to quickly go to another one. Let me see, I have underwater.
This is San Antonio's Fox News at 9.
Who've spent years working with robotics, it's a dream come true.
Yes, this is the ultimate. Making something that will work on its own without your assistance, but only because you've programmed it, you've told it how to work. It's a lot of fun.
These robots are equipped with navigation, sonar, cameras, sensors, and most importantly, a microprocessing system, essentially a brain that allows it to talk and work with other robots.
Suppose if there is a
Here's
rock,
the
if one
Kranti.
finds if there is a rock, you should not hit the rock. So it will communicate with the other robots. So, okay, fine, there is something ahead. So please choose your path to go somewhere. It's called distributed intelligence.
You'd be amazed at what an army of these robots can do working together without putting people in harm's way. Missions ranging from underwater inspections to border security, exploration, and even search and rescue. Let's say I was a diver stranded underwater. A swarm of robots just like this one would be able to find me and cover a lot of ground using not just cameras for visual proof, but also metal detectors to find any sort of metal items I might have with me.
Okay, finally, just show you a shot at the UAV, which we had tested outside the San Antonio area. It has no audio. It's a spot here. It's a cloudy day. Here's some of the images from the ground.
Systems were conspicuous by their absence from your talk altogether.
Could you repeat? I'm not
Quantum information processing systems.
Quantum information processing.
They would appear to be a natural candidate for system of systems.
Yes.
During your talk, it would seem to me that they would be almost an ideal candidate. But they were not there in your
we had some discussions in Kanpur about quantum physics and quantum computing, and I have his quantum computing book, so I will read it and I will find a bridge between the two.
In fact, this group here is developing system models.
Sure.
In fact, something comparable to what you used in your systems here, that is transfer function kind of.
Definitely.
More broadly, quantum information processing.
Okay. So you think it has a good chance to solve what aspects of these problems? Can you explain to me what aspect of this problem quantum, or you can do what aspect of it? Just for my own information. Modeling. Okay.
Graph
theoretical modeling
has a lot of potential.
Absolutely. Every one of those UAVs could be a node on the graph, for example.
You see, often control engineers talk about complexity in terms of algorithmic complexity only. Whereas in quantum field theory, one knows that observer dependence and context dependence causes high-end complexity, which need to be addressed. And therefore you need to bring in quantum field theory, whether or not you are dealing with quantum phenomena, so as to benefit from those ideas.
Exactly. You see, as a control engineer struggling for the past 40-odd years with a right balance between theory and application of control. Unfortunately, in some cases, in some circles within IEEE and other organizations, they take it so far to theory, then even the control engineers no longer can understand it anymore or read it. You know, Professor Michael Attens, who's a good friend of mine at MIT, now he lives in Portugal. He is one of those who wrote all the papers for the transaction of automatic control. He said, what is this? I can't even read it myself anymore. Give it to a mathematician and explain it to me. That's not engineering anymore. Robust control is one of those. The doctor and Dr. Hadieh knows how many millions of dollars have been sent into robust control, how many real problems have been solved. I'd love to see some, you know. So you have to balance it out. And then start shooting at Lotfizadeh for coming out with fuzzy logic as a control approach. Because it works, they don't like it. Any other comments? Thank you.